Hello, everybody. Quick show of hands, who was here for Ari's talk? I'm sorry, I don't have a guitar. I'm not as cool as Ari. No, my name is Matt Ostale. I am but a humble senior technical artist at Epic Games, and to the surprise of nobody, I have more to say about performance and memory of our next-gen graphics features. I'm going to assume that we are all reasonably familiar with things like Nanite, Lumen, and virtual shadow maps, so I'm not going to get into the intro stuff. Want to give some updates on it, show you some new things, get into the weeds a little bit, so to speak, on all these features. So here's a general overview of what I'm going to do really quickly. I'm going to throw out some project settings. So Ari was talking about the Epic way. There's a couple more things I wanted to add on top of that. I also want to talk about virtual textures for probably longer than you would expect. And obviously, we're going to talk about Nanite, Lumen, virtual shadow maps, and maybe even some Q&A. And ultimately, this talk is about making efficient use of time and memory, both efficient use of time and memory on the GPU and efficient use of your time and memory as developers, right? So in the spirit of efficiency, wanted to cover some of these project settings really quickly before we get started. Wanted to have a slide that's a reference. And this is assuming that we are doing a full-blown bells and whistles, all the features, top-of-the-line UE5 title. Not totally rendering related, but I want to throw this one out first. Go into your project settings and set your startup map to nothing. Just make a new empty level, save it. That's your startup map. It improves your editor startup time, so you don't always have to load every single thing in the map every time you want to do something. And I'm assuming that we are going to be using Nanite. I'm assuming we're going to be using Lumen, and we're going to be using virtual shadow maps. So you can turn off allow static lighting because you're not baking lighting, and it'll let you also use material ambient occlusion with Lumen, which is nice. Probably not going to get to talk about these during the Nanite section, but there are a couple of project settings called reverse index buffer and depth only buffer. This basically creates a version of the vertex array for all of our static meshes in a different order so that it's more efficient to draw. For reverse index, if we're drawing stuff with a negative scale, don't do stuff with negative scale, please. So we can turn that one off, and then if we're using Nanite, Nanite is going to do a lot of the stuff that it needs to do, so we don't need depth-only buffer, and this will save us static mesh memory, especially as we start using Nanite resolution geometry. We've got millions of triangles. Those things can get pretty sizable. And then if we are using Lumen, for software ray tracing, we want to use, or for hardware ray tracing, we want to use surface cache sampling for our real-time projects. And if we're using software ray tracing, we're going to use global traces for efficiency. And of course, we will set virtual textures to enabled, right? So just to head this off, because again, I tricked you a little bit. I'm mostly going to be talking about virtual textures. But what does that mean, right? I feel like there are a lot of virtualized features in the engine, and we just kind of yada, yada, yada past the virtual part. And it's really important to understand what virtualization is in order to understand what these features are doing and why they are so efficient, and why we should be taking full advantage of them. So generally speaking, virtualization just means creating a sparse version of something so that we're only storing and using the bits of the thing that we need in working memory and not really worrying about the rest. That is the tech art answer. So imagine we have a book, right? We've got our book, and the book has pages in it, and we know all of these pages, right? But we don't want to take all of these pages and all of the text on all of these pages and load it into working memory if we are just making a book reader, right? We know what page the viewer is looking at, and we don't really care about the rest of the pages, right? We can pull those into memory as we need them. But maybe they're going to scroll fast, scroll quickly through the book. So maybe we need some information about the pages on either side of the one that the viewer is looking at, but maybe not as at a high resolution. And then if the page is all the way at the end of the book, we don't really need any information about those pages, so we can lower their resolution, and now we have a more efficient data structure for storing the relevant parts of the book and displaying them to the user. That's effectively what virtualization is doing. Why did we? And when I say we here, I'm not just talking about Epic Games. I'm talking about the games industry, everybody working in real-time graphics as a whole, why did we need to virtualize stuff? Well, back in the day, we really only had like 3 things that we had to worry about, right? Textures, meshes, and other. And then as we started getting more advanced with our graphics features, as the assets that we started generating started getting bigger, we needed more room on VRAM in memory. But it turns out that memory sizes have not been increasing at the same rate as our demands on them. And then, of course, we're also adding new features, right? Distance fields, Lumen, virtual shadow maps, runtime virtual textures. All of these features are placing demands on a not growing as quickly amount of video memory. And so we needed to virtualize it so we can make more efficient use of the memory that we have available, right? Efficiency. So the biggest offender, right, was textures. So we virtualized our textures. So that leads me to virtual textures. We've had these in the engine for quite a while, I think going back to about 4.22, but they are not a default feature. You have to opt into these. It is a project setting, and there's a little bit of extra work that we have to do to utilize these efficiently. But basically all we're doing is we create a page table out of a texture, and we're able to stream in parts of a texture at different MIP levels depending on what we need. We have a feedback pass that tells us what MIP level we need for these. And I've got a little visualization here. This is using r.vt.borders1 just to help me visualize, oh, these are all of the different tiles at all of the different resolutions, so that you can see like even some parts of a texture are not totally visible at any given time. And to give you a sense of the benefits of virtual texturing, I want to take a look at the project that we've got here. This is the Hillside sample. It is an architectural visualization and linear content project. It's not for games. It's not for real-time rendering. But importantly, it is virtual textured by default. And I want to look at, so we've got stat streaming here, and I will zoom in on this. So stat streaming, right, we've got our streaming pool. This is the default value of 2,000 megabytes. But you look at the required pool. This is how many streaming, non-virtually streamed textures that we need to load into memory into that 2,000 megabyte pool. And that is 95 megabytes, which is not a lot, right? But then we go look at stat virtual texture memory, and if we combine the total physical memory, which is all of the different compression types, and the page table, which is how we look up all of those different compression types, we're using about 500 megabytes, which is wild, right? 500 megabytes for all of the textures in this very high resolution scene. And if we go look at the total disk size, this is MIP 0 of all of the virtual textures in the project, 22 gigabytes. So through the efficient use of virtual texturing, we're able to take what could have been an out-of-memory crash if we didn't stream any of these textures, and we're getting it down, we're using only 500 megabytes to draw this entire scene, which is wild to me. So there are 2 options for virtual texturing in the engine. We've got streaming virtual textures and runtime virtual textures. What we like to say is that streaming virtual textures save you memory at the marginal cost of performance, and runtime virtual textures save you performance at the cost of memory. And we're probably more familiar with runtime virtual textures because we've set them up on our landscape. I've got a couple of videos about them up on YouTube already. So I'm not going to talk about runtime. I'm only going to focus on streaming today because this is the one that I think is underutilized right now. Because I feel like it's a little scary. It's a little different. So I want to demystify it. So all we really have to do if we are streaming our if we want to do a virtual texture, we enable it in our project settings, of course. And then in our texture asset, we can go to virtual, and we can turn on virtual texture streaming. Great, we're done. Easy peasy. Thanks for coming out, everybody. No, stick around. There's a little bit more work that we have to do, and one of the things I wanted to highlight in this section here is that this is a 2K texture, and one of the misconceptions that I think people have about virtual textures is, much like Nanite, we all thought, oh, it's only for high-resolution geometry, and then at Unreal Fest New Orleans, I had to get up and say, if it can be Nanite, it should be Nanite. I don't care how many triangles it is. Similarly, with virtual texturing, you can virtually stream textures smaller than 4K. It's not just for high-resolution textures. Does it make it easier to use high-resolution textures? Yes. It also is efficient for lower-resolution textures as well. But there's a little tricky thing that you have to do when you are using virtual textures, and you have to modify your materials a little bit. So even though I check virtual texture streaming on the texture asset doesn't mean my work is done. I next have to go to the material, and this is the default material for the hillside, and what it uses for all of its texture parameters is virtual textures. There is no option to use non-virtual textures in this material because the sampler type is set to a virtual sampler type. So if you use a virtual texture, now you can only have virtual color, virtual grayscale, virtual alpha, and so on and so forth. So this is a thing that you need to think about when you're building your projects. I'll talk about that in a second here. But you're looking at this and go, Matt, that looks like an awful lot of work. I have to go into all my textures, I have to right-click, set the value, and then I have to go into all my materials, and I have to update all my sampler types, and I thought you were a tech artist and you were all about efficiency. Well, I am. So I've got a little demo here where I've got two sets of textures and two materials. They're used in these two different material instances, and they share a base material. And what I want to demo here is I want to turn these textures virtual. But if I then change the sampler type of the parameters that reference these textures, I then have to change all of the other textures that are being used in that parameter. And again, this sounds like an efficiency nightmare. So don't worry about it, because all we have to do is say convert to virtual texture, and it's going to go up and find all the references for these textures, change the sampler types, and then find where all of the textures find all the textures that parameter references and change those as well. And you can set the size threshold. Maybe you don't want to do a 512. You definitely don't want to do anything lower than 128. So we can filter these, and I can say, okay, I want all of these to be virtual. I hit OK. I let that convert. And you see, without ever having to touch the other assets here, they are also converted to virtual texture as well. Makes things a little easier on you. But there are some things I want you to consider as you're building out your projects for virtual texturing. It is a little better if you plan on it from day one, going in, all right, we're going to do this. This is how we're going to do it. Then you don't have to then do this kind of post-conversion step, which you might miss something. You do have to make sure that you have separate default textures for virtual textures, or for all the virtual sampler types. So you want a default virtual color, default virtual grayscale, default virtual normal, and so on and so forth, so that you can reference those in your materials and not have hard references to textures in all of your parent materials. And the other sort of construction consideration I want you to make is this concept called virtual texture stacks, which is basically the unique UV combinations within a material. So I've got a little demo material here, and I've got a texture sample that's using UV0. I've got another texture sample that uses a double tiling. I've got my normal map that's using UV0, and I've got this other blend texture that's using 3x tiling. And what this ultimately ends up in is this virtual texture stacks number of 3. There are 3 different UV combinations within the material, and in order to get the feedback that we need about this material, we have to evaluate that for each of these different virtual texture stacks. But the nice thing is that if I, for example, plug the same UV thing into my normals, it doesn't increase my number of virtual texture stacks. And similarly, if I copy and paste this up here, it's the same thing. It also does not increase the number of virtual texture stacks. But then if I want to tile my normal 4x, that will increase my number of stacks. So a thing to keep in mind as you're building out your materials. So when I say that streaming virtual textures save you memory at the cost of performance, there's two sides of this. There is a CPU cost and there is a GPU cost. On the CPU side, we need to do a little bit of work to figure out which MIPS and tiles need to be uploaded to the GPU, right? That's, hey, what page are we looking at? However, this cost isn't really all that extreme, and a lot of this work is handled off the main thread. It's not handled on the game thread. One of the costs is going to be uploading stuff to the GPU. There are some console variables to control that. There is r.vt.max uploads per frame, and that will affect both runtime and streaming virtual textures. But with runtime virtual textures, we want to keep our uploads fairly low, because if we have too many uploads, then we're rendering our landscape material too many times and we lose our performance gains there. So we can separate runtime virtual texture uploads from streaming virtual texture uploads with r.vt.max uploads per frame.streaming. Again, the CVARs from this are all going to be in the links at the end of the show. Don't worry about writing them down. So that's kind of the cost on the CPU side. It is fairly negligible. On the GPU side, obviously I have to talk about this, there is an additional cost to using virtual textures. And the short of it is that we have to first sample the page table to figure out where in memory all of our tiles are actually stored. So there's like a little layer of indirection, a little bit of an extra sample. So you do have to keep that in mind. Not necessarily going to be a huge issue if we've just got a bunch of regular texture samples in our default material, but if you're using like a virtual texture flow map to look up another virtual texture, to look up another virtual texture, to look up another virtual texture, and so on and so forth, that can get a little squiggly. But again, I really want you to profile. Ultimately, at the end of the day, I want you to know what is causing the problem. Don't immediately assume that, oh, I'm using streaming virtual textures, so I'm going to have bad CPU. Profile, try it out, learn from your project. Your project will tell you what the problem is. So virtual textures are great, and we're going to use them in our projects, but we have to do a little bit of creative accounting because I mentioned earlier, right, the default value for the non-virtually streamed texture streaming pool is 2,000 megabytes, but we're only using 100 of those right now. So we've got a really big truck that is carrying not a lot of weight, right? So we gotta move some stuff around. And maybe as we're building out our projects, r.streaming.pool size can come down because we don't really need it. And in fact, if you hide screen messages and you lower that number, the engine will tell you if something is wrong. You'll get that thing in the top left corner that's like streaming pool over budget, X number of gigabytes. It's going to tell you where that high watermark is as you're testing things out. Similarly, with virtual texture memory, as of 5.4, we've got a fun little thing now that lets us figure out what those high watermarks is. But the tricky thing with virtual textures is that each of the different compression types have their own pools. It's not just one pool for all textures. It's a different pool for DXT5, BC4, and so on and so forth. And in 5.4, we added a fun new thing called, we added a project setting for virtual texture pool sizes. And maybe you've seen this as you're flying around in your updated 5.4 projects. You'll see this like resizing virtual texture streaming pool in the bottom right corner, little toast pop up. So what that's asking you to do is go into your project settings and go to the virtual texture pool settings, and it's going to have this transient pool list down here. And that's keeping track of the high watermarks, and it's going to say, hey, copy these values into this fixed pool. So transient, that's only for that session. Fixed pool is the actual thing in your default engine INI. So you can see the high watermark for DXT5, that's going to be like our base color textures, that was 105 megabytes. Okay, I'm going to set my high watermark to 105 megabytes. BC4, we needed about 39 megabytes before things got oversubscribed and so on and so forth. I, of course, have turned off pool auto grow in editor because it does hitch a little bit every time it has to do that. I wanted to keep this presentation tight. And then there's a default size in megabytes, so if you wanted to start out your project and have a really high value of that, you could absolutely do that. But then as we get toward the end of the project, we want to make sure that we are using just as much memory as we absolutely need to, so that we're, again, making efficient use of our video memory. Because, again, generally speaking, we don't want to use a pickup truck to carry around a pebble, right? That's not an efficient use of that space. But similarly, we also don't want to use a coupe to carry around a boulder, because when we try and fit too much into a pool that cannot hold it, we've all seen this before, right? We all know what this is. This is a dropped MIP. We had to lower the texture resolution so that we could fit everything into our available space. And with virtual textures, sometimes we'll just drop a texture out of the pool altogether, and then you start getting popping, right? That's not really, nobody enjoys that. The other thing I wanted to call out with virtual texture memory, and memory in general, is a new tool in 5.4 called the Render Resource Viewer. And this is great, because this is all of it. This is everything that we need to represent the scene in video memory all at once. And you can see, oh, I've got my virtual texture page pool. I've got my Nanite streaming pool, my TSR history color buffer. And I can see, oh, I've got my virtual physical texture. So these are the different compression types. There's also the virtual page table. This is how we go reference all of that stuff in memory. And this is going to give you a lot more information about all of the different features that are using memory in your project. It's because it's not just textures and meshes anymore, right? So I mentioned we need to get feedback from the GPU about what MIPS and tiles we need to load into memory at any given time. And we do this in about one in every 16 pixels. That's controlled by r.vt.feedback factor. So, hey, every 16 pixels, we're going to jitter this around and we're going to pick which pixel we want to test, and then we'll figure out if we have the right tile for that, queue the upload, and so on and so forth. And pages are being stored in memory after they've last been seen, because sometimes if you're looking over at the right side of the room and then you really quickly move over to the left side of the room, okay, we don't see those textures anymore, so we can drop them and we can make room for something else. But then if you really quickly turn back over, in the amount of time that it took me from go right to left to right, I don't really have time to re-upload that texture, and we still want it to be there when we look back at it. So there is basically a timer, which is represented by all these little gradients timing down. That is r.vt.page-free threshold. And there's a weird thing that can happen where if sometimes the feedback factor and the number of stacks and the number of textures that we've got in the scene, we don't quite hit everything. And so we start dropping textures that are actually visible in the scene. And what you will see where this will come up is the map requests value in stat virtual texturing will start to go really high in a scene that is static. Because if you're not moving your camera, theoretically, everything should settle, right? So just wanted to throw that out there, a fun little pro tip, thing to watch out for with virtual texturing. But how are we feeling? Feeling good about this? Everybody's seen you use virtual textures. We're feeling great. We know where our project settings are. We're good to go. Okay. So let's talk about Nanite. So Nanite is also a virtual feature. It is virtualized micropolygon geometry. Really quickly, quick overview. Nanite is great. It's going to give you near pixel perfect lotting of your geometry. And what that means, what I mean by that, is that even though you might have 10 million triangles in your static mesh asset, in your FBX, it is very rare that you will ever be rasterizing all 10 of those millions on the GPU in the frame that you're looking at, right? It's trying to be efficient about using the GPU. So what it does, the way it does this, is it pre-simplifies your geometry from the disk in clusters of about 128 triangles, and then it will simplify those clusters down so that we can, okay, these 10 clusters were together. Now we can simplify those down to one cluster based on the max edges per pixel, max pixels per edge. And these are basically virtual texture tiles, right? These are, discrete units of the geometry that we can stream in and out based on our feedback. And as an aside, if you are using Nanite, I highly recommend also using virtual shadow maps. Those two systems work together very, very well. And they're meant to work together so that you get really nice high-resolution shadows fairly efficiently using Nanite. So there's some fun updates, some fun new stuff that has come online with 5.4 that I wanted to talk about very, very briefly. The first is Nanite spline meshes are now production ready. And so I've got here a little example. I've got my spline mesh, and I want to conform this sidewalk to the road. So what I'll use is our modeling tools and the draw spline tool. I'll grab that existing blueprint, and now I can click in the world and draw out a spline, and it's going to conform that sidewalk to the terrain, and I'm feeling really happy about that. So I hit accept, and then I can go into our Nanite mask visualization. There we go. So you can see I have a spline mesh, and it is Nanite. Huzzah. The other fun thing that we've got is Nanite tessellation. This is still experimental, but I do want to talk about it, and Aaron Langmead is going to talk about this a lot more later today. Generally speaking, this is a sometimes food. It does add a cost to rasterizing all of these triangles because we have to figure out how to tessellate and then displace them. But there are some interesting memory benefits that we can get out of this level of tessellation. So I've got two rocks from Quixel Megascans here. The one on the left is Nanite resolution, and the one on the right is medium resolution. And to show you nothing is up my sleeve, here's the wireframe view mode. These are the respective base resolutions of these meshes. And then if I turn on tessellation, so I do r.nanite.tessellation1, and then if I go into my Nanite triangles view mode, we're going to see that they are now uniformly tessellated. And the benefit here is that I can use maybe a 4 megabyte or 1 megabyte displacement texture to displace a 50,000 triangle mesh, and that's going to have ultimately a lower disk footprint than a 2 million triangle base mesh with Nanite. So if you're worried about your hard drive space, there might be some benefits here to evaluate based on, okay, what resolution do I need? How detailed do I need this geometry to be, and so on. The other fun one that I don't think a lot of us have really talked about yet is a new checkbox we added to Nanite, the Nanite settings struct. So by default, when Nanite is simplifying things together to generate those clusters, it will interpolate linearly the attributes of all of the vertices. So as we collapse two verts together, we want to, and this is a desirable behavior generally, unless we need to do something like vertex animated textures, where we need an explicit UV coordinate to look up an explicit value in a texture. So what we did was we added a checkbox that said, hey, don't do that. Pick a UV value when you are interpolating or when you're collapsing that geometry down together. What this means is now we can do vertex animated texture techniques using Nanite. And what this looks like, I used the anim to texture plugin on this on these Twinmotion assets to generate a little crowd, and I turned them all to Nanite, and now I have a little Nanite crowd, which is a lot of fun. General recommendation here, though, because these are all going to be programmably rasterized, basically treat them like trees, right? We got to make sure we have WPO disable distance set. We're probably going to want to use a fairly current gen resolution character mesh. We don't want to go, 3 million triangles for each of these, but this is now an option for rendering things like crowds. So those are things that we have to opt into. We might have to do a little bit of setup for. The next couple of things I want to talk about are things that you get for free with 5.4. So the first one, as my colleague Graham Wildahl discusses in his recent GDC 2024 talk, Nanite GPU-driven materials. The first one is that now Nanite shading takes place in compute shaders. So we are finally using compute shaders to shade pixels, which is wild. The benefit here is that, as I talked about in New Orleans last year, if you had a bunch of materials referenced in your scene that weren't visible, those created what were called empty shading bins. Empty shading bins had a little bit of a cost because we had to transition between each of those. And now with compute, we can compact all of those together. And now we are only worrying about shading the pixels and the materials that are actually visible on screen. This is great. This reduces a bunch of overhead, and you don't have to do anything for this. The next one is, as he was building all of this out, we also got variably rate shaded Nanite, which is a really big improvement because it means that now if you are shading a 2x2 quad, you actually get to use all of those pixels instead of doing a 2x2 quad for each pixel so that you could get the derivatives. The thing you have to watch out for is that if you're using things like DDX or DDY in your materials, that breaks variable rate shading, so you can't use those in your materials. And you're like, man, I really don't want to, I'm not looking forward to having to go through each of my materials to figure out where all of these things are. Don't worry, I got you. So all we have to do is r.nanite.visualize.advanced1. CVAR's in the links at the end of the show. And that's going to give me a few more view modes for Nanite, and one of them is no derivative ops. So this is showing me all of the materials in blue that don't use explicit derivatives like DDX or DDY, and in red, all of the materials that are. So now I can go find those materials and evaluate them. Do I really need to be using DDX, DDY? And this is going to help you make sure that you are able to variably rate shade your Nanite, which is great. The other new view mode that has come online with Nanite that I wanted to highlight is the pixel programmable view mode. So this is showing us all of the materials that are masked, pixel depth offset, or dynamic displacement. So again, there is going to be a cost to this, and pixel programmable is always going to be evaluated, so we got to go figure out what's going on over there. But this is going to give you a little bit more information into digging into your Nanite performance, which is the next thing that I wanted to talk about. I think in New Orleans, I didn't really talk about a philosophy of how to debug the performance of Nanite, so I wanted to do that, if you'll bear with me. Because one of the things that I have found in talking to people is there is a sort of instinct to over-optimize and to start optimizing for problems that are not there. So I want to talk about how we can look at Nanite from a performance debugging point of view. So step one, is it Nanite? I've talked to some people before. They're debugging their machines like, oh man, Nanite, we really gotta solve this problem with Nanite. Nanite's causing us a bunch of performance problems. Like, great, what's your Nanite budget? How many milliseconds are you willing to spend on Nanite in a 16 millisecond frame? Is Nanite over that? Great. Okay, now we can start talking about it. And there's two places that we're going to look for this. The first place we're going to look for this is programmable rasterization, and this is the Nanite viz buffer. So if we do a GPU visualizer with Control-Shift, this is going to show me in the scene Nanite viz buffer. So this is usually where we see some problems with Nanite performance. This is where and programmable rasterization specifically. So if we want to see more information about that, we just have to do r.nanite.show mesh draw events 1. And then if we do another GPU visualizer, I can dig into that scene value and go to Nanite viz buffer, draw geometry main pass, and this is going to show me hardware rasterize and software rasterize. And if I expand this out, this shows me fixed function rasterization, which is all of the stuff that is opaque and non-deforming, and all of the materials that are programmably rasterized for whatever reason, right? WPO, max materials, and so on. So this gives me some information, and I can look at these values and go, okay, is my issue in fixed function, or is it in the accumulation of all of these raster bins and their various evaluations, right? So now I can figure this out. Now, the way that I kind of look at this, if I wanted to kind of diagnose it further, start figuring out the binary tree, the first thing that I'm going to do is go Nanite visualization, evaluate WPO. So this is going to show me all of the things that are going to be programmably rasterized. We have to evaluate all of the vertex shader 3 times per pixel and so on and so forth. If this view is mostly red and my programmable rasterization cost is high, I might then assume that the issue is with masked materials. I might have a lot of masked materials in my scene, and I can see that if I go into our pixel programmable view mode. So wow, there's a lot more pixel programmable stuff than is evaluating WPO. So maybe the first thing that I'm going to look at is my masked materials, right? Okay, so maybe it's not either of those. Maybe you have no pixel programmable, you have no vertex programmable. Great. So then we start looking at fixed function rasterization, which is all of the stuff that is opaque and non-deforming. And one of the things that you might look at here is Nanite overdraw. And you'll notice that I've been talking about Nanite performance for a bit, and this is the first time that I'm bringing up overdraw, because I feel like one of the things that I see happening a lot is we go Nanite visualization, overdraw, and this is our first port of call to say there is a Nanite performance issue. And that's not really how I want you to be using this view mode. I want you to use this view mode as I have noticed a performance problem, and this is a tool to diagnose where that issue might be coming from. This is not telling you there is an issue with Nanite overdraw. It can tell you where that issue might be and how you can resolve it. So it's really easy for us to look at this view mode and go, there are white pixels. White pixels is a lot of Nanite overdraw, so I immediately have to start solving for that. I would prefer if you didn't. But I want to talk about Nanite overdraw because there's a few different things that we can do when we're building our content to mitigate the issue out of the gate so that we never have to worry about that, or we can worry about it less. So we've got these shipping containers here, and I want to talk about these. So we go into wireframe, we can see that these are really long, thin triangles, which is not really great for Nanite. And one of the reasons for that is we go to Nanite visualization clusters. You can see that the whole side of this shipping container comprises a few clusters, and those aren't going to partially occlude, right? And one of the really cool things about Nanite is we can occlude clusters. We don't have to rasterize clusters that aren't visible. But if these clusters are partially visible, you can see this shipping container is almost totally overdrawing this other shipping container because those clusters are partially visible. So even if I go along here, right, I can see that top edge, so I have to rasterize all of the stuff underneath, right? So maybe there's a better way we can be building our content so that we can better leverage things like, or we can improve our Nanite overdraw without necessarily going in and immediately over-optimizing everything. So what I've got here is I used our geometry scripting tools to somewhat crudely remesh these and uniformly remesh these so I could demonstrate a thing that you can do as you're building out your content. So I can go to my clusters view mode, and you can see that now I've got individual clusters scattered all over the surface so that if I go into Nanite overdraw, what we'll see is that the shipping container behind is being partially occluded, right? As we move around, as those clusters become invisible, we're not rasterizing them. This is great. We want this. And you can also see that even the one shipping container itself is more effectively partially occluding itself. This is, right, we can build our content thinking about cluster culling, and it'll give us more efficient Nanite overdraw performance. There are a couple of things that we can do to cause more problems with Nanite overdraw, and it's interpenetration. So if I jam a bunch of static meshes together, they're partially overlapping. Clusters are called based on bounds, so if you have stuff that's really closely stacked, like these shipping containers, we can't cull those clusters, and so we get even more overdraw. So as you're building out your worlds, making sure that you're not jamming a bunch of static meshes together, we can ensure that we are not going to run into these kind of overdraw issues, right? So this is a preventive measure. The other thing that I see a lot with Nanite is greeblies, right? I want to scatter a bunch of stuff over my sci-fi spaceship or something like that. I have very crudely mocked up an example here with some new assets from Quixel Megascans that look a lot like greeblies. But if I go into Nanite overdraw, you might think like, oh man, that's going to cause a lot of overdraw. But because they're sitting on a large flat surface, that large flat surface is going to occlude everything underneath, so we don't end up with a huge stack of Nanite overdraw, which is actually kind of nice. But we do, maybe if we get down to a glancing angle, we can get some hot spots, but those hot spots are going to be isolated to that kind of parallel on-side view, okay? So finally, now we've gone through Nanite Viz Buffer. Now we're getting to Nanite Base Pass. And the short of it is, prior to variable rate shading and compute shading, this gets more compact. It does get a little trickier. But the short of it is, if Nanite Base Pass is out of the budget that we have defined for Nanite Base Pass, because we're defining our budgets early, there are two things this could be. It is either the number of shading bins, so you have a few thousand of those. We can always see that with Nanite stats. So if I just do a little Nanite stats, that's going to bring up these numbers. I love numbers. And I can see the total number of shading bins. I can then subtract that for the number of empty shading bins. And I can start figuring out, all right, how many shading bins, like how many draw calls am I doing effectively, right? So I'm going to do Nanite stats off. The other possibility here is your materials are expensive, right? This is when we are filling the pixels with Nanite, or when Nanite is drawing the materials to all of the pixels that it rasterized. So then we could finally start talking about material performance. Okay, so really quickly, I'm going to talk about Lumen. Quick refresher, this is a performant real-time ray trace global illumination and reflection system. It is tracing pixels per ray, not rays per pixel like a normal ray traced system, so that we can do things more efficiently. I want to talk really quickly about some performance considerations and demo a little bit of debugging with Lumen issues. So in October last year, I said if you were going to do a 60 frames per second game, you should budget about 4 milliseconds for Lumen. If you're doing a 30 frames per second game, you should budget about 8 milliseconds, and I left it at that, and I yada past it, and I didn't really explain what I meant by this. So and it gets tricky because Lumen is running asynchronously on consoles, so it's hard to give specifics here. And Lumen also comprises multiple passes and features: Lumen scene lighting, diffuse indirect and AO, reflections, lights, and so on. So what I actually mean by this is if you turn Lumen off, r.dynamic global illumination method 0, r.reflection method 0, you should see frames that are about 4 or 8 milliseconds faster. So what can we do about that? There's a couple of things I talked about in October last year, right? We can move stuff out of the Lumen scene, set things to visible and ray tracing false, set things to affect dynamic indirect lighting false. Those kinds of things are things that we can do to make it more efficient to render the Lumen scene. But maybe we want to talk about reflections, because one of the things I talked about was r.lumen.reflections.max roughness to trace. Because if our reflection cost is really high, we got to figure out what's going on there. Well, great news, in 5.4 we added a new view mode, which is the performance overview mode, and this is showing me all of the pixels that are tracing dedicated reflection rays. And I might look at this and go, wow, why are all of the trees, so things that are in green are are using the subsurface or two-sided foliage shading model. Those have a separate console variable, r.lumen.reflections.max roughness to trace for foliage. And I'm like, wow, why are all of these trees casting dedicated reflection rays? And I'm like, oh, the weather shader is making them low roughness because they're wet because it just rained. Well, I don't really need to trace dedicated reflection rays for these trees, right? I'm not going to see anything in those reflections. So I can go r.lumen.reflections.max roughness to trace for foliage. Maybe I set that to 0. I don't need trees to reflect anything. And now I'm tracing fewer reflection rays. And then I look at the rest of the scene and I go, wow, for what I'm looking at, that is a lot of dedicated reflection rays. And that's not maybe the most efficient use of my GPU time. And so I can start to look at this and go r.lumen.reflections.max roughness to trace. Maybe I set that to 0.2. And I noticed, maybe my puddles got a little smaller, but those puddles had a really high roughness fall off so that we were getting that value. But maybe I might go into that material and kind of clamp it down so that I'm only, I have a bigger area for those puddles. But like the side of this building over here, this building was tracing reflection rays. That's a bit silly to me. Maybe we don't need to do that. So if your Lumen reflections are pretty high, that's a place to look. We can talk more about it. There's also a Lumen performance guide that is in the links at the end of the show that's going to go into way more detail than I have time for. I also wanted to talk very briefly about how we can debug Lumen, where we can look to figure out why a problem is happening with Lumen and how we might resolve it. Not going to get into super specifics. We are running out of time, but I wanted to give you a little hint about where we can start looking. So maybe the keen-eyed among you have already noticed this issue right there. So keep your eyes right there. You see that subtle flicker? There's just like a, on, off, right? I'm pretty sure it's Lumen. So what I might do to figure out if it's Lumen dynamic global illumination would be r.dynamic global illumination method 0. And now I'm not using any global illumination. Oh, I know why that doesn't work. We'll talk about that later. So, see me after class. So I know that this is a Lumen issue. And I want to figure out what it is. Well, there are two different ways that Lumen traces rays and gathers information for its global illumination. There are screen traces and world traces. Screen traces are just grabbing values from pixels on the screen. World traces are pulling values from the Lumen scene. And the first thing that I recommend you do if you're debugging Lumen is figure out which is which, right? What is the binary search tree? So I'll go into Show, I'll go to Lumen, and I can turn off screen traces. And if I turn off screen traces and the issue goes away, I know it's screen traces, right? And this is where I might start looking at console variables like r.lumenscene.probe screen probe gather, which are too innumerable to list. The other possibility is that it is going to be global traces. So I'm going to turn our screen traces back on. And where I might start looking here is in the Lumen scene view mode. I might look at this and see, wow, there's some stuff. Some of this stuff is maybe too black. I would expect some of this stuff to be a little bit more visible. Why is that happening? So I can go then look at the surface cache view mode, and everything that is in yellow, Lumen said, I don't need to worry about this. I'm going to drop it out of the Lumen scene. Everything that is in purple was drawn into the Lumen scene, but those pixels were not rendered to because maybe our surface cards were not set up correctly or our mesh is too multivariant and complex. And so Lumen wasn't able to draw to those pixels, which is why something like the side of this catwalk over here is not showing up correctly in the Lumen scene. Okay, I think I'm going to do it. All right, got to talk about shadows. Can't not talk about shadows. Virtual shadow maps are our new system for UE5. Instead of writing out a bunch of shadow depth cascades every frame, we virtualize those shadow pages, which lets us cache these pages and only update the parts of the shadow map that we actually need. And to give you a overview of that, right, we talked about virtual textures. Those have tiles. Similarly, virtual shadow maps have pages. And each of these little squares we can think of as effectively a virtual texture tile. So a couple of quick things I wanted to mention about this new to 5.4. There's an update to static versus dynamic caching. So if you're unfamiliar, by default, virtual shadow maps will say, all right, I've got things that are static. They are not invalidating the shadow cache every frame. So those get drawn into the static pages. And then I have stuff that do invalidate cache pages, and those are going to go into a dynamic virtual shadow map cache. So they're separate, right? But if something prior to 5.4, if something ever invalidated cache page, it would always be treated as dynamic. So if I walk up to a tree, it invalidates cache pages. Great, it's dynamic. But then if I walk far away from the tree beyond its WPO disable distance, because we set our WPO disable distances, it's not invalidating cache pages, but it is still being treated as dynamic, and it's still going to be drawn into dynamic cache pages, even though it doesn't actually need to be. So we've got a console variable for that, which is r.shadow.virtual.cache.static separate .frame static threshold, CVARs in the links. And this is similar to the r.vt.page threshold. This is basically saying, okay, how long should something not invalidate cache pages before I turn it to static? Because when I turn it to static, there's a little bit of cost there. When I turn it back to dynamic, there's a little bit of cost there. The other change to virtual shadow maps is how we treat the WPO disable distance. So I set up this Ferris wheel here. It is totally animating with WPO so that I could contrive this example. And I've set a really short WPO disable distance on it so I can demo this. So WPO disable distance, if I get far away from this thing, it will stop animating, and it will then of course it will stop invalidating shadow cache pages, which is desirable behavior. But what would happen prior to 5.4 is if we had this thing casting a really long shadow, like at dusk or dawn, if it was close to us, it would invalidate cache pages all the way out the length of its shadow, which is kind of counterintuitive. That's not really how we would want to do this. We would think that the WPO disable distance would have an effect on how far it can invalidate cache pages, which is what we did for 5.4. So let's go back to that. Let's get closer to it to get it animating. And so what the new system does is it takes the WPO disable distance, it rounds up to the nearest clip map level, which if we look at clip map mask level, so we can see, all right, so it's going out to here, out to here, out to here, and then I'm going to round up to green, from green to red, and then if the shadow is casting into red, don't invalidate any of the red cache pages. There's a LOD bias to this, so it'll actually go out a little bit further, just to make sure that you don't see the artifact that I'm about to show you, because I want to show you what this looks like, so if you ever see it, you know what it is. So I've got the WPO disable distance set really short. The LOD bias on the WPO disable distance is set to 3, so we're going to go 3 beyond that by default. But then if I do r.shadow.virtual.clipmap.WPO disable distance .LOD bias, and I set that to 0, hopefully you can see half of the shadow stopped animating. Do y'all see that? Right? So if you ever see this like artifact where just like half the shadow is moving and the other half isn't, that's what is going on here. It's a combination of the WPO disable distance on the primitive and the LOD bias in that console variable. So it gives you a little bit of control there. So I'm going to bring that back. But I contrived this example, short WPO disable distance, set that CVAR really, really low. Not necessarily what you're going to do in production, but thing to watch out for. Other thing I want to talk about is virtual shadow map performance, and again, kind of how we want to debug that. Firstly, before you start optimizing VSMs and cache invalidations and things like that, start with the Nanite Viz buffer, because if we go into our GPU visualizer, I can go to shadow depths, and we can see that in render virtual shadow maps Nanite draw geometry, this is also a Nanite Viz buffer pass. So if you optimize your Nanite Viz buffer, you will also have benefits when you're rendering virtual shadow maps, which is great. The other thing that you can do, again, as we're debugging the Nanite visualization tree, as we're debugging our Nanite programmable rasterization, there's a virtual shadow map Nanite overdraw view mode for virtual shadow maps from the perspective of the directional light. And you're going to see, like, not everything is rendering in this view because only those cache pages are the ones that are being invalidated. Okay. And of course, like I said, I'm a numbers guy. I want to show you some numbers. So one of the things that we can do with virtual shadow maps, r.shaderprint1, and then we can do r.shadow.virtual.showstats1. And this is going to give us a bunch of numbers on our screen that's going to show us the number of physical pages, the amount of non-nanite geometry that's being drawn, which is fairly expensive with VSM, the number of static pages that are being invalidated, the number of dynamic pages that are cached and invalidated. This is going to give you some numbers to help you figure out where to look. Should I be focusing on dynamic invalidations or static invalidations, and so on. So turn that one off. Okay. So what have we learned today? Well, we learned some project settings that are going to make things a little easier for us. We learned about setting up virtual textures and the considerations that we're going to need to make as we are building them out. We also learned how we can debug Nanite performance. We learned about some of the new features with Nanite, like tessellation and spline meshes. We got some tips for debugging Lumen, right? Setting our screen traces or world traces, or which console variables we might want to look at. And we learned some fun things about virtual shadow maps and how we might debug some of those issues so that we can figure out the extent of our invalidations. Very, very quickly, there are some other talks I want you to go to. So if you leave right now, you might be able to make it to adding a rendering fast path without breaking Unreal Engine. You might also want to go to optimizing survival games for mobile, or again, Aaron Langmead is doing an artist's guide to using Nanite tessellation. Tomorrow, I just love talking about PCG, so definitely check out First Steps to Advanced Development. There's also optimizing the game thread from our friends at Tanglewood Games, and of course, performance budgeting in a post-poly count world, because asking how many triangles you can have for Nanite is the wrong question. So definitely go check that talk out. All right, we are at time, so I'm going to give you a choice. It is lunchtime. I know we're all hungry. If you would like to leave for lunch, feel free to leave, but nobody is in this room for the next hour, so I am happy to keep taking questions. So if you want to leave, feel free. If you want to ask questions, head up to the microphones. On that, that's all I got. Thank you all so much for coming out. I really appreciate your time. You have been a lovely audience.